So that video was not Shutterstock. That was actually Neuralink. So that's actual video from the company. So if you want to get a sense for what it's like to work on Neuralink, that video is indicative of the atmosphere of Neuralink. It's an incredibly talented team, and you're going to hear a lot from them tonight. So we're going to actually go quite into depth on what we're doing, why we're doing, how we're doing it, and I'm just incredibly impressed with the caliber of the talent at Neuralink. And in fact, the main reason for doing this presentation is recruiting. So we really want to have the best talent in the world come and work at Neuralink. Anyone that's interested in trying to solve this problem, and that's actually the primary purpose for this presentation. So. Okay, so the why of Neuralink, just to go over it, is I think it's if you think about your limbic system and your cortex, your limbic system is kind of your primal needs and wants. It's like where your emotions are coming from, and then the cortex is like the thinking, planning part of your brain. And I haven't met anyone who wants to get rid of either the cortex or the limbic system. So clearly they work together well. Even though your cortex is in principle far smarter than your limbic system, everybody wants to keep the limbic system and their cortex. So hopefully we can have a tertiary layer, which is the kind of a digital superintelligence layer. And in fact, you already have this layer. So it's your phone, your laptop, and the constraint is just how well you interface the input and output speed. So the output speed is especially slow since most people are typing with thumbs these days. So you have a very slow output speed. Your input speed is much faster due to vision, but the thing that will ultimately constrain our ability to be symbiotic with AI is bandwidth. So in the limit, after solving a bunch of brain-related diseases, there is the existential, it's mitigation of the existential threat of AI. Or, yeah, this is the so creating a well-aligned future that's the idea.
Of nearly 100 billion cells called neurons. Neurons come in many complex shapes, but generally they have a dendritic arbor, a cell body called a soma, and an axon. The neurons of your brain connect to form a large network through axon-dendrite junctions called synapses. At these connection points, neurons communicate with each other using chemical signals called neurotransmitters. Neurotransmitters are released from the end of an axon in response to an electrical spike called an action potential. When a cell receives enough of the right kind of neurotransmitter input, a chain reaction is triggered that causes an action potential to fire, and the neuron to in turn relay messages to its own downstream synapses. Action potentials produce an electric field that spreads from the neuron and can be detected by placing electrodes nearby, allowing recording of the information represented by a neuron.
I thought we'd play that twice. So good you have it. Well, I think like a lot of people in the audience, there's a wide range of knowledge about neurons. I mean, some people will view the brain as like this incredibly mystical thing that cannot interface with the brain, and then some people are aware of the brain stimulation, such as occurs for Parkinson's patients. So, trying to address the broad range of understanding. I mean, neurons is essentially. There's the whole idea, what if we were just a brain in a vat? This is often posed by philosophers, except we are a brain in a vat, and that's it. That vat is our skull. Everything that you perceive, feel, hear, think, it's all actual potentials. It's all just it's neural spikes, and it feels so real. It feels very real. But these are all impulses from neurons, what's called a spike. And our goal is to report from and stimulate spikes in neurons, and do so in a way that is orders of magnitude more than anything that's been done to date, and safe and good enough that you can. It's not like a major operation. It's sort of equivalent to sort of a LASIK type of thing. So where you can sort of sit down, the machine does this thing, and you can walk away within a few hours. That's it. You're not even in a hospital. So there's basically in terms of key points that are worth taking away. The system that we designed in version 1 is capable of on the order of 10,000 electrodes. So each chip, which is 4 by 4 millimeters, is capable of 1,000 electrodes, or has 1,000 electrodes, and we think doing up to 10 is feasible. So this is in contrast to the best FDA-approved system, which is like a Parkinson's deep brain stimulation thing, which would have on the order of 10 electrodes. So the system, even in version 1 that we're going to unveil today, is capable of 1,000 times more electrodes than the best system out there, and they're all read and write. So this is really quite, I mean, for something to be 1,000 times more than what is publicly approved is quite a big difference. And this will get better with subsequent versions. This slide may seem a little generic, like everything's about robots, electronics, and algorithms at this point, but not threads. So the Enlightenment transcendence. There's actually I wasn't transcendence. So there's very tiny threads that are about a tenth, or roughly, of the cross-sectional area of a human hair. So they're extremely tiny threads. In fact, the threads that we have, even in version 1, are about the same size as a neuron. So if you're going to stick something in your brain, you want it to not be giant, you want it to be tiny, and to be approximately on par with the things that are already there, the neurons. So this is about the size of a neuron, each thread. And then you really need this to be done with a robot, because it's very tiny and it needs to be very precise. So you don't want to pierce a blood vessel. So when you insert each thread, the robot looks sort of basically through a microscope and inserts each electrode specifically, bypassing any vascular, any kind of blood vessel, making sure so they can be inserted without causing harm, with minimal harm. Yeah, that's zero. You won't notice it. That's the important part. You won't like it. Yeah. One cool thing. So it's the algorithm. Just to give you a sense of scale, this is how tiny the threads are. That is not even a big finger, that is a small finger. So these threads are just like way smaller than hair, and there's 1,000 of them. Now this is what the robot looks like. It's sort of quite a complex device, but it all comes down to a very tiny point. looks like. You see the robots on the left, and then the what looks like the needle is insertion next to a penny, but in fact the actual needle that gets inserted is way, way tinier. It's that little tiny thing where the arrow is pointing. That's actually the size of the needle, about 24 microns. Extremely, extremely small. It's so small you can't really even see it in the picture with the penny. And then this is ran on uranium. Really. That's agar. So you get a sense for the robot doing the electrode insertion. That's a very zoomed in view. So they're all very, very tiny, and the robot is very selectively applying them very delicately. And then this is what the looks like. Actual potentials. So each one of those represents one electrode. So there will be up to 10,000 of these lines. So I guess it's very difficult to take. There's going to be there's a lot more in this presentation. So in terms of things that I think are important to bear in mind, this I think has a very good focus, which is to cure important diseases, and ultimately to help secure humanity's future as a civilization relative to AI. The threads are very tiny, and there's a lot of them, and they're very carefully placed, and the operation on a per chip basis, it involves just a 2 millimeter incision, which is dilated to 8 millimeters, and then the chip is placed through that, and it goes back to being 2 millimeters, and you basically glue it shut. You don't need a stitch. So, and then the interface to the chip is wireless. So you have no wires poking out of your head. Very, very important. So it's basically Bluetooth to your phone. But we'll have to watch the App Store updates for that one. Make sure you don't have a driver issue. Updating. So the key is like this is something that is going not stressful. Our goal is not stressful to put in. Should work well, hopefully. We check it out very closely before obviously FDA approved. And it's wireless. So this thing has tremendous potential, and we hope to have this inspiration in a human patient before the end of next year. This is not far. And then, as I mentioned earlier, the main purpose of this presentation is recruiting. We need very talented people in all these areas. So it's a lot of very talented people that needed to make this ultimately successful. And then, speaking of talented people, we need to hand it over to Max.
Thank you. I'm Max Hodak. I'm the president of Neuralink. I remember a couple of years ago when we started talking about the idea of Neuralink and that there might be a company and whether this was even a good idea. My first reaction was that I wasn't sure that this actually was a good idea. And I think Elon has this incredible optimism where he appears through these magic constraints and show you that really a lot more is possible than you really think is today. And you have to be very careful claiming that something's possible that would be limited by a law of physics or you're going to end up looking stupid. And so I've wanted to build a neural interface is really to make a central goal of my life, basically as long as I can remember. I think like you talked about AI being the last invention that we have. I think that identity might be like the first invention anyway. So like the next chapter of it's just really, like as you alluded to earlier, everything about your experience, your thoughts, your memories, it's all in your brain representing defining statistics, action, and control. So, alright, so what is a BMI? We'll get to this really, like, fairly quickly, I think. So you start with hopefully a brain and a machine. But the machine is just a stand-in for the outside world. It could be another brain, it could be software, it could be a robotic arm. But you want to receive energy from that world and impart through the senses, like vision and audition, impart energy back into the world through things like motor control. And that language that they use to communicate, putting aside the target for a second, it's very important to understand what that is. Because people often go to talk to my dog and these things, but it's important to understand what that language is. That language, in the most general sense, is information. To a first approximation, everything is information. But we just consider here the information represented in neurons. And so consider two like toy neurons. One, so these lines are imaginary examples. Imagine a neuron that fires very regularly, like a metronome. It doesn't tell us anything. There's no information conveyed in the signal. On the opposite end of the spectrum, imagine a neuron that fires completely randomly. This also doesn't tell us anything. This also doesn't carry any information. Now we know that these two different cases are not what neurons do, because if you fit a model from recording neural activity to behavioral things like a cursor of a patient or a subject that's implanted and correlate these, then you can build a graph that looks like this. And this is a figure from a classic paper in this field, from like the academic heritage in this field from 2003. I think that actually some of the authors of this paper in the audience today. And you can see that the x-axis is number of neurons, and the r is the goodness of fit. And so as you add neurons, the quality of the model improves. This tells us that neurons and their spike trains carry information about things. Here Austin puts really quickly, that's because what they were fitting here was just 2D cursor control, which has simple dynamics. And if you have tasks that are more complicated, then you need more neurons. So the classic definition of information is a difference that makes a difference. It's just some piece of information or knowledge that tells you something. It's like a very abstract concept, but it's such, like information theory is such a deep rabbit hole. I haven't seen it before. The original paper in mathematical theory of communication is like, it's very readable. I highly recommend it. You can start seeing information everywhere. It will totally change the way you view the world, because the world is information, as we talked about before. And understanding information also gets this question of, well, why do you have to have an analytical device? What do you use or optimal thing? And the answer, of course, is like, well, these are different information carriers, and what information are they carrying? And we know that, like, if you open a back issue of the Journal of Neuroscience and you understand how some species of bird encode sound localization or something, you'll find a discussion of spikes. And we, as far as we know, everything that we care about is found in the statistics of spikes. So that's what we focus on. There are other things like fMRI or EEG. These are different information carriers, different information, which we think is, which we believe is impoverished relative to spikes, and that's the scientific consensus. And so the question for all these different things is, well, what information is found in your carrier? We focus on spikes, that means we have to be inside the brain, because there's no ceiling everywhere on that with respect to the light gravitation, your perception, your thoughts, everything. Clear output, like your body loss. And so why does that mean that you have to be inside the brain? So we want spikes. Well, people have studied, if you take a neuron and you put an electrode on that specific neuron, so you have a ground truth electrical potential of that one neuron, and then you place an extracellular electrode nearby, which is where our electrodes in the UTRA and other people are like, we're not in the cell, we're in the cells. And then you measure how far away from a neuron can you be when you know what the ground truth spike activity is and you no longer see the spikes. And it turns out that the answer is about 60 microns, which is like 0.06. It's very small. It's a lot less than a millimeter. So you have to be firmly under the skull. Like you're not. There's no wearable that is going to get you spikes. This is a physics constraint as far as we're aware. And so now I just want to talk about briefly that there's, like, it really didn't come out of nowhere. There's a long academic heritage of research here. The cochlear implant has reached millions of patients since the 50s for deaf patients. Over 100,000 patients have received deep brain stimulation for Parkinson's and essential tremor and dystonia and other indications. And about 20 patients have received the Utah array, which is a little 100 electrode rigid metal silicon device. And even though it has very few channels, they've been able to do some really cool stuff with it. There's videos on YouTube of brain gate patients doing things like controlling tablet computers or even texting each other through Utah arrays just from these small little electrodes. And so there's many of the people on the team really came from this academic work. I got my start working in the lab at university studying how mappings between brain and the screen space change. So if you make it so the joystick goes like the picture goes sideways and the keyboard instead of up, and how does the brain change that representation? So the point is that there are lots of people that have been looking at this problem from lots of angles for decades, and we're in the greatest sense clearly on the shoulders of giants here. And so the question is, why not use one of those devices? Why not use a Utah array or a deep brain stimulator and a pulse generator? And it's just, in the Utah array case, the rigid sharp metal electrodes produce a fairly strong response. And this doesn't end up hurting the patient, but it does mean that we lose the ability to record single spikes over some period of time, which we run in a couple of years. There's also a big percutaneous connector through the scalp. So you plug in big external electronics, and you're never really confident that the risk of infection is gone for the duration you have the implant. Deep brain stimulators solve a very different type of problem. They're very effective for some Parkinson's patients, but they have only a couple electrodes, and they're really geared towards injecting large amounts of current, not recording single spikes. So they're really very different. DBS is really just a very different type of platform for doing a very different problem. So we had to go back to the drawing board and start over with some built-in that met the goals that Elon laid out for us. We knew, as Elon mentioned, that whatever we built, we wanted it to be completely wireless. Any connectors or wires coming through the skin, it had to be something that would last for a long period of time, not something that you had to take out at 2, 3, or 4 years in. It had to have practical bandwidth. So we talk about high bandwidth or ultra-high bandwidth. Like, what matters is that for the task that you're after, there's practical bandwidth that allows you to effectively do that thing, whether that's person control or typing or robotic and it has to be usable at home. It can't be something that you go into a clinic at the hospital for 2 hours a week and really tight supervision with technicians, plug in the amplifiers and turn it on. That's the same that you can do. And so 2.5 years ago, we were nowhere close to any of that. This is a photo of some of the prototypes that we've gone through over that time. So we started on the far left. That's an entirely passive board that has 64 electrodes on it and connects to connectors that go to big external amplifiers. And then we added integrated electronics with our first custom chip that's also 64 channels. And then there's a big leap to the device that Elon showed a photo of earlier. That has 3,072 electrodes in the fully implantable package, with just a USB-C port coming out. And then we took a step back in channel count because we were optimizing safety, longevity, and bandwidth altogether. So in order to optimize some of the other things, we moved from easier to manufacture system as 15 or 36 channels in the USB-C port. And those last two are the focus of the paper that we released today. And so we've learned a lot from these. We've recorded a lot of data through these. Like, these are actually used every day at Berlin to record neural data and work with it. And they taught us a lot about the architecture that we think was the basis for our first human product that we're calling N1. And the central component of that is the N1 sensor. It's a little hermetic package. It's when it's fully assembled, this is missing an outer mold. It's into an 8mm diameter, 4mm tall cylinder. And each of these has 1024 electrodes, and we can stim and record through every one of those channels. Opening it up a little bit, you can see there's a thin film that has the thread that Elon talked about, which is the wisp going off to the side. There's a hermetic substrate, and then that gets welded later to a package that goes over top, and that's connected to our custom electronics. We'll go into more detail. We'll have the technical leaders that work on each of these talk about these in more detail over the rest of the presentation. So yeah, I mean, this is just to not to belabor the point that really, these things are very, very small. They're not. You can't manipulate this. This is one photo. This is not two photos coming together. And you really can't manipulate these with your hand. That part at the top is just a backing material that's a surgical package, and they're peeled off. Threads are peeled off one at a time by the robot to place in the brain. And it's a surgical robot. And the first impetus for this is just you have to place these threads. You manipulate these threads, you use a robot, and then that can turn out to grew into understanding where the blood vessels are and changing the tissue and the surface of the brain moves because you're breathing and your heartbeat. There's lots of complexity in this incredibly high entropy substrate. And it's not all offloaded to the robot. The robot's under the supervision of a human neurosurgeon who lays out where the threads are placed, but it would not be, the surgery is not possible without the robot. And so the N1 implant, we can place, as Elon mentioned, many of these, possibly up to 10. In one hemisphere, for our first patients, we're looking at four sensors, 3 in motor areas, 1 in a somatosensory area, which are connected via very small wires to the scalp conductive coil behind the ear. And that connects wirelessly through the skin to a wearable device that we call the Link, which contains a Bluetooth radio and battery. And this is importantly the only battery and radio in the implant. So if you take this off, the implant shuts off. And if there's software upgrades or security issues, it's much easier to upgrade the firmware on the pod than it is to try and change the implant. It will be controlled through an iPhone app. You don't have to go to a doctor's office and have an exotic programmer to configure it. And the first thing you have to do is learn to use it. I mean, imagine if you've never had arms, and then suddenly you have an arm, and you have to pick up the glass on the table. It's like not a cognitive task. You're just like, you can't think your way through that. And so it's kind of a tricky experience at the beginning, where like patients, at first it just wanders around, and then they figure out how to break this imagery, and they learn how to control it. And that's like it's a long process. It's like learning to touch a woodplate piano. And so for the first product, we're really focusing on 3 distinct types of control. The first is giving patients the ability to control the mobile device. Because we heard over and over again from patient groups that if you have to have a caretaker around and press buttons for you, what's the point? You might as well have to do your thing. You have to get self-sufficient using the devices on your own. And then redirect the output from your phone to a keyboard or a mouse on a normal computer. It'll just show up as a Bluetooth mouse or a Bluetooth keyboard, like any keyboard or mouse that you can use on your computer. And as Elon mentioned, this is a forward-looking statement. There's a whole FDA process we have to go through. We haven't done that yet. This is like, these are aspirations. But we are working as hard as we can towards our first in-human clinical study next year. And again, these are plans, but the primary indication for that will be complete paralysis by upper cervical spinal cord injury. And we're expecting that those patients will get 4 1024 channel sensors, 1 each in primary motor cortex, supplementary motor area, dorsal motor cortex, which is motor planning areas, and closed loop feedback into primary somatosensory cortex, which is like when you type or walk with a pen, you don't visually guided movements. Your body has all these senses of where it is in space and pressure and temperature and lots of other feedback. And we think for really high fluent control, you have to provide that back to the brain for the synthetic implants also. And of course, fully wireless and able to use it. There's a huge difference between something that you get from these 2 hours a week at the hospital versus something that you're living with every day and your brain is adapting to as much as the device is adapting to your brain. And so to bring up the other colleagues, this team is like incredibly lucky to get to work with this team. We're going to go into a little more detail on and the decoupling implantation from the electrodes is incredibly important. The reason that you have physicians where things like these tungsten microwires get rejected is they're stiff and sharp and they tear the brain, and they have to be because they have to get into the brain. And so if you can decouple the process of getting it into the brain from what is left there, where it can be much softer and have material properties like the brain, and maybe coated in things that help recognize it as itself, that's really important. And then the thin film polymer leads, the threads themselves, are really cool material science, and we'll go into more detail on that. And then we'll also talk more about the chips, and then a little bit more on just the neuroscience of how information is represented in firing statistics in the brain. And so with that, I'd like to welcome Dr. Matthew McDougall.
Thanks, Max. I'm Dr. Matthew McDougall. I'm the head neurosurgeon at Neuralink. When I'm not at Neuralink, I'm a brain and spine surgeon here in San Francisco at CPMC, California Pacific Medical Center. Before that, I was at Stanford, where I worked in labs that implanted and designed advanced brain-computer interfaces. One of the things that I found most fascinating was that brain-computer interfaces are really, really important. And so, to bring up the other colleagues, this team is like incredibly lucky to get to work with this team. We're going to go into a little more detail on the I originally became a neurosurgeon because I wanted to help people live happier, healthier, longer lives. I've been humbled in practice by how powerless we are to treat many of the most debilitating neurologic diseases. People afflicted with spinal cord injury, schizophrenia, autism, and a host of other neurologic conditions have far too few options. I work with Neuralink because we, for the first time in history, have the potential to solve some of these problems. Before we get to how we get the device in, we have to talk about our guiding principle at Neuralink: safety. Everything we do at Neuralink is filtered through the question, will this make me more likely to want to get one? Will it make me more likely to recommend this to my family and friends? This approach impacts every design decision we make. So while for the immediate future, Neuralink's devices will only be intended for patients with serious, unmet medical needs, difficult to treat diseases, also to understand them better. I hope you find this as exciting as I find it. If you feel you might be able to help us, don't hesitate to contact us. To talk more about the technology behind all this, I'd like to introduce Vanessa Tolosa, Director of our Neural Interfaces Group.
Hi, I'm Vanessa Tolosa. I lead the Neural Interface Group at Neuralink. Our team consists of engineers and material scientists who are responsible for making the probes that get implanted into tissue, the packaging for the electronics, and integrating these two components together. We also do all the testing and characterization of these parts. Before joining Neuralink, I led a neurotech team at Lawrence Livermore National Lab. There we worked on a wide range of neuroprosthetic technologies that were used both in the academic and clinical setting. I decided to join Neuralink because I saw an opportunity to take all of this exciting work that we were seeing in neurotech research and actually make them accessible to patients at a much faster time rate than what medical device companies have traditionally been able to do. With that in mind, at Neuralink, we set out to create a fully implantable neural interface with thousands of channels that are capable of single spike resolution. This device must last a long time in the body. To do this, it must be small, flexible, and made of biocompatible materials that will minimize the brain's immune response. To protect the electronics from the caustic environment of the body, it must have airtight packaging, also known as hermetic packaging. The device must also be able to both record from and stimulate neurons. This is essential for a highly functioning BMI. Finally, the manufacturing process must be scalable and capable of making micrometer-sized features consistently. Currently, there are no research or commercial devices that meet all of our requirements. So we built out of microfabricated film polymers. Just like in semiconductor chip manufacturing, we use a layer-by-layer process that generally consists of 3 repeating steps. We're either always depositing material, patterning material through photolithography, or etching away material. Depending on the complexity of the design, these steps can be repeated over 100 times. And to make things more challenging, we are limited to materials that are safe for the body. In our current design, we have a 3-metal layer process that results in a 5-micron thick and 10 to 40 micron wide probe. To give you an idea of how small this is, red blood cells have a diameter of about 8 microns, and an average strand of hair is about 100 microns. Yet in the small footprint, we're able to fit our electrodes, our wires, and insulation for each of those wires. With microfabrication, we can drive features down to the size of an electron beam. So this is great because we want to make our probes as small as possible. Essentially, we want it to be invisible to the brain. But there are other factors that limit the size of our probes. For example, as we make the wires smaller, it increases the resistance of those wires. And as the resistance increases, it makes it more difficult for us to separate our signals from our noise. Similarly, there are other technical challenges and trade-offs that are related to higher channel counts and manufacturing yield, electrode size, and material and tissue safety. At Neuralink, we have an incredible team that's been tackling these challenges and have been able to make high channel count polymer probes. In this image is a silicon wafer that holds 10 of these arrays, these polymer arrays. In this design, each of those arrays has over 3,000 channels. So what that means is in this one wafer, we've manufactured over 30,000 electrodes and over 30,000 insulating wires. This is something that can't be done with the way current medical devices are being made. That rainbow effect is caused by the small feature sizes on these devices that are interacting with the nanometer size wavelengths of light that are reflecting off of them. If you were to zoom in on the ends of one of these arrays, you'll see this region where we put all of our electrodes. So each of these vertical filaments that end in a loop is what we refer to as a thread. And each of these threads can be placed independently into the brain using a robot during surgery. This design is called linear edge. It's one of over 20 designs that we've made for our R&D work. We've progressively been increasing the number of electrodes per thread without significantly increasing the width of each of these threads at the base. We've been able to do this by adding layers and reducing the size of the wires down to as small as 350 nanometers. This is less than the wavelength of visible light. Because we're using a lithographic process, essentially if we can draw it, we can also make it.
At a much faster time rate than
so on one end of our probes are the electrodes. On the other end are where we connect the probes to the electronic package, or to the electronics through conductive feeders. This substrate is part of the hermetic electronics package. Standard methods of connecting the probes to the electronics package usually involve some kind of large plug-in type connector or a polymer-based glue that bonds the two components together. But as we increase density and decrease the footprint, it becomes impossible to achieve hermeticity in standard medical device connectors. This is due to several reasons. One of them is how these substrates are currently manufactured. Hermetic feeders consist of holes that have been packed with conductive materials and are embedded in an insulating substrate. As you drill more holes and pack them more tightly together, these brittle substrates, typically made of ceramics, become more susceptible to cracking. Also, as you make the holes smaller, it becomes more difficult to fill them with this conductive material without getting non-hermetic voids.
Just like in semiconductor chip manufacturing,
standard processing also requires exposure to high temperatures, typically over 700 degrees Celsius. At these high temperatures, the coefficient of thermal expansion, or CTE mismatch, between the insulator and the conductor can cause circumferential cracking or interfacial gaps during the cooling phase. We're able to get around these problems by developing a new process.
In our current design, we have a
So rather than making the probes and then the substrates and then connecting them together, instead we microfabricate them together into one monolithic component. This provides a tight seal at densities that current methods with standard materials for medical devices can't achieve. So far we've used this process to make a hermetic thin film substrate with over 1,000 connections over a 2.4 millimeter by 2.4
So this is great because
millimeter
we want to make our
footprint.
probes as small as possible. Essentially, we want it to be invisible to the
Next, we assemble the
But there are other
electronics
factors that limit the
and
size
then
of
also
our
attach
probe.
a wired
For example,
lid
as we make the
using a
wire smaller,
laser
it
welding
increases the
process.
resistance of
These
those
two
wires.
steps
As
have
resistance increases,
required
it makes it more
a lot of
difficult for us to separate
internal
our signals
development
from our
as well.
noise.
The result
Similarly, there are other
is the
technical
sensor that's ready
challenges
for
and
final
trade-offs
assembly
that are related
and
to
implants into the
higher
body.
channel count and manufacturing
Next,
yield,
you'll hear from my
electrode
colleague
size, and
DJ
material
about our custom electronics.
At Neuralink, we have an incredible team that's been tackling these challenges and have been able to make high
Thank you,
channel
Vanessa.
count polymer
My name is
probes.
DJ Saul. and I'm the Director of Implant Systems at Neuralink. My team focuses on building chips and systems to get neural signals recorded from our electrodes out of the brain, and also to put information into the brain. Before Neuralink, I was at UC Berkeley, where I co-invented NeuralBus, which is a technology to power and communicate with small implantable systems using ultrasound. Typical chip lifecycle from design to verification to tape out is approximately 1 to several years. At Neuralink, we had the ability to co-design our chip with the rest of the system. And the tight feedback loop from this organization has enabled our small team of analog and digital chip designers to tape out a new design every 3 months on average. That means over the past 24 months, we've done 8 tape outs in total, representing 15 different chips that have been designed, fabricated, tested, and used in development. The artwork that you see on the top of the slide is of some of the actual chips that we made so far. For any custom chips we make, the architecture can vary substantially, but the basic ideas are the same. Neural signals recorded from the electrode typically look like the one on the slide. And in order for us to extract the information that we care about, we need to first amplify, filter, and digitize those neural signals, and use digital logic to process and send out the bits we want for BMI. We also need ways to diagnose any issues with our electrodes and be able to drive stimulation engine to inject charge to the brain when required. Our latest chip is called N1 System on Chip, and it is physically small, measuring only 20 millimeters squared or 4 by 5 millimeters. It is low power, highly configurable, and it has 1,024 simultaneous record and stimulation capable channels, and it has on-chip spike detection. To dive deeper into N1 SoC, I like to highlight 3 key innovations, and they are 1. Analog pixel, 2. On-chip spike detection, and 3. Stimulation on every channel. The first is analog pixel. Before we can convert analog neural signals into digital bits, we need to amplify and filter them. And this is where the analog pixel comes in. We want to have 1 analog pixel per electrode so that we can configure them independently. So in the case of N1 SoC, there are 1,024 analog pixels. Analog pixels also take up a significant portion of the physical space on the chip, and how well they work determines both the signal quality and the characteristics of the overall neural interface. The goal of analog design is for analog pixel design is to make it as small as possible so we can fit more, as low power as possible so we generate less heat and have longer battery runtime, and as low noise as possible so we get the best signal. Now, the challenge here is that these goals are at odds with each other. For example, we want to achieve lower noise on the amplifier so that more spikes can be detected. But as transistors get smaller, it becomes harder to get lower noise while keeping the power the same. Since the start of Neuralink, we've gone through 3 major revisions to the analog pixel, progressively improving both the size and power while maintaining performance. Over the past 24 months, we had 7-fold improvements in the size of the analog pixel, and our latest pixel on the right is at least 5 times smaller than the known state-of-the-art of similar architecture with 1 pixel dedicated per electrode, as published in the academic literature. Second innovation is on-chip spike detection.
My name is DJ Seo.
Once the signals are amplified, they're converted and digitized to zeros and ones by our on-chip analog to digital converters. As you'll hear in a second, spikes or action potentials shown in this slide are often critical for certain BMI tasks. Currently, there are several different methods for detecting spikes, such as thresholding, or more sophisticated methods such as principal component analysis. At Neuralink, one of the robust ways that we came up with is by directly characterizing the shape, and it's worth noting that this is different than template matching in that it gives us more information in a general way. In certain cases, we can actually identify different neurons from the same electrode based on their shapes.
A new design every 3 months on average. That means
our analog pixel can capture the entire neural signals sampled at 20,000 samples per second with 10 bits of resolution, resulting in over 200 megabits per second of neural data for each 1,024 channels that we record. In our previous systems that you heard about, we were able to stream this entire broadband signals through a single USB-C connector and cable, and we performed real-time spike detection on an 8-core machine running on Optimus C code. Now, we wanted to completely eliminate connectors and cables for N1, so we had to modify our algorithms to fit into the hardware by scaling both, making it both scalable and also low power.
We also need ways to diagnose any issues with our
And then we were
electrodes
able to also
be able
implement
to
this
drive
algorithm in our
the
N1
stimulation
system.
engine to inject charge to the brain when
Our
required.
algorithms can compress neural data by more than 200 times, and it only
Our
takes
latest chip
900
is called
nanoseconds to
N1
compute,
system on chip,
which is
and it
faster
is
than the time it takes for the brain to realize it
measuring
happened.
only 20 millimeter squared or 4 by 5 millimeter.
Finally, it was important for us to enable stimulation from every channel that we can record from and make it configurable and high
And
resolution.
it has 1,024 simultaneous
To make this work, we
record
custom
and
designed
stimulation
stimulation
channels.
engine for electrical stimulation that can
And it has
coexist
one chip
alongside our
spike
analog
detection.
pixels.
To dive
Our
deeper
stimulation
into
engine
N1
has
SoC,
0.2
I'd like to highlight
microamp
3
of
key
amplitude
innovations.
resolution and
They are
7.8 microsecond of time
One,
resolution.
analog pixel.
There is a 16:1 ratio
One
of
chip spike detection.
electrode to stimulation engine, so we
And
can't
3,
stimulate every channel
stimulation on
simultaneously.
every channel.
But we can within each stem pulse, usually
The
in
first is
milliseconds,
analog pixel.
and we can also stimulate any
Before we
combination
can
of
convert
64 channels
analog
at the
neural
same time.
signals into digital bits, we need to amplify and filter them.
So in summary,
This is where
looking
the
through our
analog
N1 SoC,
We want to have
it
one
has
analog pixel per
1,024
electrode so
analog
that we can
pixels
configure
that we
them
can record
independently.
from
So in the
simultaneously
case of N1
with
SoC,
7.2
there
microvolt
are
RMS noise,
1,024
while
analog
only
pixels.
consuming 6.6 microwatt of power.
Analog pixels also take up a significant
It has
portion of the
on-chip
physical space
analog
on
to
the
digital
chip.
converters,
And how well they work determines both
on-chip
the
spike
signal
detection
quality
that can compress
and the
neural data
characteristics
more than
of the
200
overall
times,
neural
and it
network.
only takes 900 nanoseconds to compute.
The goal of analog design is
Stimulation
for analog
engine
pixel
with
design
0.2 microamp
is to
of
make it
amplitude
as small
and
as possible
7.8
so we can
microsecond
set
of time resolution.
as low power as possible so we generate less heat
And finally,
and have longer
diagnostics for
battery runtime.
electrode and impedance measurement.
And as low noise as possible so we get the best signal.
All of these functionalities that I
Now,
outlined are
the challenge
integrated
here
into a single
Is that these goals
4
are
by
at
5
odds with each
millimeter
other.
silicon die.
For example, we want to achieve lower noise
Next,
on the amplifier.
my colleague Flip
so that
will
more
tell you
spikes
more
can be
about what can be
detected.
done with these signals.
But as transistors get smaller, it becomes harder to get lower noise while keeping the power stabilized.
Thanks, DJ.
Since the start of Neuralink,
My name
we've
is
gone
Philip
through
Sabis,
three
and I'm the
major
senior
revisions
scientist
to
at
the analog
Neuralink.
pixel,
Before
progressively improving
Neuralink,
both
I was
the
at
size
UCSF,
and
where I was
power
a
while
professor of
maintaining
physiology.
performance. Over the
There,
past
for
24
16 years,
months,
I
we
ran a
had
lab
sevenfold
that studied
improvements
how
in
the
the
brain
size of the analog
processes
pixel.
sensory and
And our
motor
latest
signals.
pixel on the right
We developed
is at least
new
5
neural
times
technologies,
smaller than the known
and
state-of-the-art
we studied how to
similar
take
architecture
those
with one
tools
pixel
and use them
dedicated
for
per
neural
electrode,
engineering applications.
as published in the academic literature.
Today I'm going to tell you about how it is that we can
Second
use those
innovation is
amazing
on-chip spike
devices
detection.
that Vanessa and DJ just told you
Once the
about
signals are
to
amplified,
communicate
they're
with the
converted
brain.
and digitized to zeros and ones by our on-chip
Now
analog
specifically, I
digital
want to tell you
converters.
about two things.
As you'll hear in a second, spikes
First,
or action potential shown on this slide are often
I want to
critical
show you
for certain PMI
that
tasks.
the work that we're doing doesn't come out of thin air.
Currently, there are
We're
several
building
different methods
on
for
over a
detecting
century
spikes,
of
such
neuroscience
as
research,
thresholding or more
decades
sophisticated
of neural
methods such
engineering
as
research.
principal component analysis.
These provide a
At
solid
Neuralink,
foundation
one of the
for the sorts
robust
of things
ways
that
we
we're
came up
talking
with
about.
is by directly characterizing the shape.
Second,
and it's worth noting that this is different than template matching in that it gives us
I-
more information in a general
I
way.
want to show you why we
In
believe
certain cases, we can actually
that
identify
even more
different
advanced
neurons
applications
from the same
are
electrode
possible
based
with
on
more
their shape.
advanced devices. Now, when Elon
Our
contacted
analog
me
pixel can
over
capture the
2.5
entire neural
years ago
signals
now,
sampled at 20,000
and
samples per second with
told
10
me
bits
about
of
his vision
resolution,
for the company,
resulting
I
in
knew
over
that I wanted to
200
join
megabits per second
for
of
these two
neural
reasons.
data
Because I
for
knew
each
that
1,024
the
channels
technology was at a
that
point
that we record.
where with the right team and the
In our
right
previous systems that you heard
vision,
about,
and a
we
long-term
were able
vision,
to stream this entire
we could do the
broadband
sorts of
signal
things that we're
through a
talking
single
about.
USB-C
And I
connector
knew
cable.
that
We
with
performed
that team,
real-time spike
we could do
detection
things that no one had even
on
dreamed about.
an 8-core machine running our optimized
Okay.
code.
So the first thing I want to show you,
We wanted to completely
is a video.
eliminate connectors and cables for N1.
many of you who are seeing this
modify our
have seen
algorithms to
videos like this
fit
before,
into the
so you know what it
hardware
is.
by scaling
But if you
both,
don't know what this is,
making it
I have the
both
distinct
scalable and
pleasure
also low power.
of telling you that right now what you're looking at is the brain at
And we
work.
were able to also implement this algorithm in our N1.
This is in fact traces of a bunch of
Our
electrodes
algorithms can
that came off of
compress
one of our
neural data by
devices,
more than 200
a bunch of
times.
electrodes from a single
And it
thread.
only takes 900
And,
nanoseconds to compute.
Each trace
which is
shows you
faster
a voltage waveform
than the time it
in
takes for the
time
brain to realize
as it's
an
coming
outcome.
off of one of those threads. Now, if we focus in
Finally,
on
it was
one
important for
of
us
those
to enable
traces,
stimulation from every channel.
the first thing you may notice is that there are these big voltage deflections that happen periodically, and these are the spikes that Max and Elon and others have talked about. These spikes occur, again, when a neuron has an action potential. And this is the fundamental element of communication within the brain. And this is the thing that we want to tap into. This is what we want to do.
Electrode to stimulation engine. So we
Now, as
can't
DJ just
stimulate
told
every
you,
channel simultaneously.
we have algorithms that can
within
detect these
each
spikes
stem pulse,
in real
usually
time
milliseconds.
as they're happening.
And we can also
And that allows us
stimulate
to
any
collect data
combination of
that looks
64
something like
channels
this.
at the same time.
This is what we call a spike raster. So each
in
row
summary,
there
looking
represents
through our
one
N1
channel of recording,
SoC,
and time goes from
it has
left to right.
1,024 analog
And each of those
pixels
little
that we
tick
can
marks
record from
is the time of a single
simultaneously
spike in
with
action.
7.2 microvolt RMS noise.
Right. So
while only
presumably there's
consuming
some information
6.6
somewhere in there.
power.
How do we get at it? What are we going to do with it?
It has on-chip analog to
Well,
digital
for the first
converter.
application, which Max told you about, which
On-chip
is
spike detection
allowing
that
paralyzed
can compress
individuals
neural data
to be able
more
to
than
control a
200
computer.
times, and it only
What
takes
we want to do is we
900
want to
nanoseconds
reach
to compute.
into primary motor cortex and record the activity
Stimulation
that's
engine
happening
with
there.
0.2 micrograms
Primary motor
of
cortex is the
amplitude
part of the
and
brain
7.8
that sends
microseconds
signals
of
down the
time
spinal
resolution.
cord into the muscles to drive movement. Of course, it does that
And finally,
with action
diagnostics for
potentials.
electrode and
And in particular, we want to record from the hand and arm
all of these
portions
functionalities
of primary motor.
that I outlined are integrated into a single
So imagine
4 by 5 millimeter silicon die.
Imagine that you have a person
Next,
sitting
my
holding a
colleague
mouse,
will tell you
and
more
they're sitting
about
still,
what can be done with these
and then they make an outward movement with their mouse, and then they reach back. What would you see in the brain? Well, here's a synthetic neuron. I made these data up, but
My name is
it gives you the idea. Here's a synthetic neuron that shows that in the background activity, when the person's at rest, maybe there's some firing. But when that neuron, when that person reaches outward, that neuron starts to fire a lot. And when he reaches back, the neuron becomes quiet. So this is what we call a neuron that's tuned to a particular direction of movement.
And we studied how to take
Now, maybe we'll record from another neuron, and this neuron may have a different pattern. It may be tuned to the return movement and not to the outward movement, so it fires more on the return.
amazing devices.
What if we asked the person to do that movement again?
Communicate with the brain.
What we would see is a similar pattern of activation. So the neuron on top still fires more for outward movement, and the neuron on the bottom still fires more for the return movement. But you notice that the patterns are different. And that's because neural activity in the brain is random. It has stochasticity. Which means that even though the person may be intending to do the exact same thing from one movement to the next, the neural code, the neural representation at the level of the individual neuron is noisy. And this is just one of the reasons why we need to record from lots of neurons in order to be able to gain a high fidelity readout of what the intention is. So okay, so let's say we record from a bunch of neurons. It might look something like this. If you look at that, you might think that looks pretty messy and it's not clear what's going on. But I'm going to do a little trick. I'm going to take those neurons and I'm going to rearrange them so that they're in the order of the tuning that they have. Look, just as I told you about those two neurons. And if you do that, look what happens. Now sudden instruction emerges. And I think you'll agree, looking at that there's information in that stack of neurons that tells you about the movement. And that's exactly what we want to do. We want to do that kind of magic in an automated way to read out the movement. The way we do that is by building something that we call decoding algorithms. These are mathematical algorithms that we tune based on data like these to be able to take in just those rasters of spiking activity and output the movement that the person wants to. Okay, so for these little fake data, I built a very, very simple decoder, and sure enough, it's able to capture the intended movement. This is what we want to do on a bigger scale. Now, you might say to yourself, I don't understand. You're talking about moving, but I thought it was about paralyzed people, right? So how does that work? Well, it turns out we know from a lot of prior research that even if you're not actually making the movement, even if you're just thinking about the movement, or even if you're watching someone else make movement, the cells in motor cortex respond in a similar way. So we can build up these decoding algorithms just from those kind of data. And then a paralyzed person can think about moving the mouse and the cursor will move. Now,
spikes occur again when a neuron has an actual
this kind of decoding has been done in a fair number of academic labs, including my own before I came here, and in humans in academic studies.
We have algorithms that can
What we want, what Neuralink's goal is to be able to do this with a clinical device that people can take home and use on their own, and then there's orders of magnitude more channels, orders of magnitude more neurons that will be put in front. With that, we think that people will be able to get naturalistic control over the computers, not just a mouse, but also a keyboard, game controllers, and potentially other
there's some
things.
information somewhere in there. How do we get it? What are we going to do with it? Well, for the first application,
I told you about
which
the
Max
arm
told
and
you
hand
about,
area of
which
motor
is
cortex.
allowing paralyzed
But
individuals
the
to be able
devices
to
that we're
control the
talking
computer.
about,
What
because
we
of
wanna
their
do is
high
we wanna
bandwidth
reach into
and
primary
the
motor
ability
cortex
to
and
tailor
record
the
activity
location
that's
of each
happening there.
individual
Primary motor
electrode
cortex is the
to
part of
a
the brain
person's
that sends
individualized
signals down the
cortical
spinal cord
anatomy.
into the muscle
We
to drive
should be able to reach anywhere in
does
motor
that
cortex.
with action potential.
So, for example,
And,
there are areas
in particular, we want to record
at
from
the base of motor
hand and
cortex
arm
that are responsible
primary motor
for
cortex.
driving activation of the speech articulators. There was a
imagine-
recent lovely study from UCSF that showed
Imagine
that from
you have a
activity like
person
that, you can actually
sitting holding a
decode
They're sitting still,
speech. So
then they make an outward
you can
movement
decode the
with their
movement
mouth,
of the articulators,
then
and
they
from
reach
that,
back.
you can create synthetic
What would you
speech.
see in the brain? Well,
So
Here's a-
potentially
here's a
with a device like
synthetic
this,
neuron. I made
you could
this data
restore
up,
speech
but-
to a paralyzed person
but it gives
who's
you
no
the
longer
idea.
able to talk.
Here's a synthetic neuron that shows
But there's
that,
no reason in principle that we can't
in the
reach
background
all of
activity,
motor cortex.
when the person's at rest, maybe there's some firing.
And
But when
that would
neuron-
give us
when that
access
person reaches
to
outward,
any movement
neuron
that a
starts
person
to
thinks
fire a
about,
lot.
any movement at all.
And when he
A
reaches
person
back,
could imagine
the neuron
running
becomes
or
flat.
dancing
So this
or
is what
even
we call
kung fu,
a neuron that's
and we would be able to
tuned
decode that
a
signal.
particular direction of movement.
So that could give a paralyzed
maybe
person
we'll record from
the
another
ability
neuron,
to control,
and this
say, for
neuron may have a
example,
different
a
pattern.
3D
It may be
avatar that
tuned
they could
to
use
the
for
return
online
movement
gaming
and not to the
or
outward.
sports.
So it fires more
It could allow them to
return.
control a wide range of assistive
What if we ask
robotic
the person
devices.
to do that movement
And
again?
ultimately, if and when
What we
the
would see
technology for
is a similar
spinal
pattern of
cord,
activation. So the
nerve,
neuron on top
or muscle
still
stimulation
fires more for
gets
outward
far enough,
movement.
ultimately,
Neuron on the bottom
it could
still
be
fires
used
more for the return
to
movement.
restore
But
that
you notice the
individual's
patterns are
control of their
different.
own body.
And that's because neural activity in the brain is random. It has stochasticity.
I've talked about
Which
readout,
means that
but
even though the person may be
remember we want
intending to do the
bidirectional
exact
information.
same
We don't
thing
only want to
from
read
one
information
movement
out of the
to
brain,
next,
we want to be able
the
to put it
neural
back
code,
into
the
the
neural
brain.
representation.
To
at the
some of
level
you,
the
that may
individual
seem a
neuron
little bit
is
fantastical, that you could write
And this is just
information
one of the
into the
reasons
brain.
why we need to
But
record
actually,
lots
the
of
basic
them
building
in
blocks of
order
that
to be able to
technology
get
are already
a
there.
high fidelity readout of what the intention is.
This is the same
So, okay,
image
so
that you
let's say
saw
we
before
record
of an
from a bunch of
electrode
them.
next
It
to a
might look
cell.
something like that.
It turns out if you pass
If you look at
a
that,
tiny
you might
amount of
think that
current
looks
through
like
that
a message.
electrode,
It's not clear what's
what happens is
going
that you activate
But
cells
I'm
nearby.
going to do a little trick. I'm going
You
to take
cause
those
them
neurons, I'm
to
going to rearrange
fire an
them
action potential
so that they're in
one
the
or
order
one.
of the tuning that they have.
And
What this
that is
essentially
the
what those
technology that is
If you do
already
that,
being
look what
used
happens.
widely outside
Now
the brain,
suddenly structure
say, for
works.
example, for cochlear
And I think you'll
implants,
agree, looking
which
at
have been used
that,
for decades
that there's
to restore
information
hearing
in
to
that
death,
stack of neurons
and more
that
recently,
tells you about
in
And
the
that's exactly
eye
what we want
to
do. We
restore
want to do
vision
that
to
kind
the
of
blind
magic
in a
an
fairly
automated
rudimentary way,
way
as I'll
to read out
tell you more
to
later.
read out the movement. The way
But
we
in
do that
addition, you can
is
use
with
this same
something that we
technology
call decoding
in the
algorithms.
brain.
These are mathematical algorithms that we tune based on data like these.
For example,
to be able
to
to
restore
take
the
just
sense of
those
touch
rasters
or to
of
restore
spiking
vision.
activity
And I'm going to tell you very
output
briefly about
the
those two
movement that
applications.
the person wants to make.
So let's start with the sense of touch. Consider
For
this
the
little bit
fake data, I built
of
this
tissue,
very, very simple
of brain that
decoder,
I've just
and
highlighted
sure
here.
enough,
It's
it's
at the
able to,
border between motor
capture
and somatosensory cortex.
This is what we want to do.
If we blow that up,
Now,
what you can see
you might say to
is
yourself,
that
I don't understand. You said
somatosensory
about moving, but I
cortex
thought it was
has a
about
very
paralyzing,
special property.
right?
It has
So how
what
does
we
that
refer
work?
to as spatial,
Well, it turns out
spatial
we
map.
know from
And what I mean
a
by
lot
that
of
is
prior
that
research
there are regions
that
that
even if
encode
you're not
the
actually
palm of the
making
hand
movement,
and
even if you're
each of
just
the
thinking
5
about
digits, for
movement,
example.
or
So
even if you're
if we were to
watching someone else
stimulate
make movement,
at one little
the cells
location,
of the
say in the
cortex
thumb part
respond in a
of
similar way.
the
So we
cortex,
can build up
the
these
person would
decoding
feel
algorithms
a sense of
just
touch or pressure on their thumb.
And then
Or
a
if we were to
paralyzed
stimulate
person,
two
think
sites
about moving thumb.
on the palm, in the palm area of cortex, you might feel a couple of points or touches on your hand. This kind of technology has been demonstrated in many
This kind
academic
of
labs,
decoding
and
has been
in a
done
recent
in
really nice paper, it was
a
shown
fair number of academic labs,
that
including my own,
with subjects
before I came here,
controlling
and
a robot
in
arm
humans in
through
academic,
BMI,
studies.
getting tactile feedback of when that
what we want,
arm,
Neuralink's
or when the
goal,
hand of that arm is
is to be
grasping
able
an
to do this
object,
with a clinical
improve the
device
ability to pick up
people can
and
take
place
home and use
objects
on their own.
with the robot.
And
So
there's
this is
magnitude
the kind of thing that can
more
really help
channels.
decode.
Orders of magnitude more neurons than we're
So imagine what we could do if we
With
were
that, we
able to
think
take
that
our
people
device
would be
and
able to
cover
get
all
naturalistic
somatosensory
control
cortex.
over the computer.
We could
Not
give
just the mouse,
rich
but
sensation
also the keyboard,
of objects, of
game
haptic
controllers,
feedback when you're
and the touch
manipulating
screen.
objects. You could maybe feel different textures. But it's not just about improving the user experience.
I told you
It's
about
also
the arm
about
and hand
getting
area
to the
of
level of
cortex.
functionality that we want.
But
Imagine for a
devices that
second,
we're
imagine
talking
typing.
about, because of their high bandwidth,
Now imagine typing with your fingers
and the ability to
anesthetized.
tailor the location
That's going to be
of
pretty
each
hard.
individual
So
electrode
that haptic
to a
feedback, that
person's
sense of sensory
individualized
feedback during
cortical
movement
anatomy.
is going to be important
We
going forward.
should be able to reach
And,
anywhere in motor cortex.
and yeah.
So, for example, there are areas
So,
at the base
that
of
sensory
motor cortex
feedback
that are
for the
responsible
hand,
for
we can
driving
also
activation of
potentially
the speech
provide
receiver.
visual feedback.
There was a recent
So
lovely study from
visual
UCSF
cortex, just like
that,
somatosensory cortex,
showed,
has maps.
that from
So
activity like that, you can
there's a
actually
spatial map
decode,
in visual cortex, which is here in orange in the
So
back of the brain.
you can-
So
you
for
can
example, if
decode
we
the
stimulate
vocally
a
articulated,
particular point
and from
in the
that,
cortex,
you can create
we might see
synthetic speech.
a flash of light in a little punctate spot.
Potentially
in
with a
front of
device
us.
like this,
And
you could
this was
restore
demonstrated
speech
many
to a
years ago
paralyzed person who's no longer
by neurosurgeons, and it's been
But there's
used
no
in
reason in
academic labs.
principle that we
And we
can't
call
reach
that little
all
dot a
of motor
phosphine.
cortex.
And if you
And
stimulate
that
another
would give
area,
us
you get a
access
phosphine in a
to
different location.
any movement that a person thinks about.
So
any movement
the
at
idea
all.
here is that you could
Person
stimulate a bunch of
imagine
different areas,
running
and you
or
could create
dancing
kind of like a
or
dot
even kung fu,
matrix
and we would
image
be able to
of the
decode
visual
that
world,
signal.
which could provide a rudimentary form of
that
vision.
could
And there are
give a
academic
paralyzed
labs
person
and even
the ability
companies
to control,
that are
say,
working
for
in
example,
technology just
a
like
3D
that.
avatar that they could use for online
But
gaming for sports.
there isn't just one map
It could
in
allow
visual
them to control
cortex.
a wide
Actually, there are a
range
bunch of
of
different maps.
assistive
This
robotic
is a good
devices.
example of how the brain works.
And ultimately,
There's a spatial map, but there are also
if and when
maps telling
technology
you about the
for
orientation
spinal cord,
of edges in the
nerve,
field.
or
There are maps
muscle
telling you about
stimulation
color.
gets far enough,
There are maps
ultimately,
telling you
it
about
could
the
be
size
used
and speed
to
of objects
restore that
moving.
individual's control of their
So
own body.
what we want is a device
Okay.
that has sensors that are small
talked
enough,
about
electrodes
readout,
that are small
but
enough,
we-
and a high enough
remember, we want
density
bidirectional
that we
information.
can
We don't
tap
really
into
want
that
to read
rich
information out of the brain. We want to
collection
be able to
of
put it back
maps
to the brain.
with our stimulation
Some of you, that may
devices.
seem a little
So
bit
that we can do
fantastical
better than
to
just
write
dot matrix,
information into the
so that
brain.
we can
But
actually create
the basic building blocks
rich
of that
visual
technology are already
feedback
there.
for the blind. That's the long term.
This is the same image that you saw before of an electrode
Let's just,
next to the cell.
again, one
Turns
more
out if you
example
pass
of the
a
way
tiny
that
amount
these
of current
devices
through that
can be
electrode,
used.
what happens is that you activate
So I've
cells
talked
in your
about
body.
recording
Cause them to
signals, and I've
fire
talked about
action potential
stimulating.
longer or many.
You can combine those two
That is the
to treat a
technology
variety
that is
of
already being used
neurological
widely
disorders.
outside the brain. Say, for example,
Max talked
what's
earlier
called their
about
implant,
deep brain
which has been
stimulation
used for decades
to
restore
treat,
hearing
say,
to
for
deaf,
example, Parkinson's
and more
disease.
recently,
And many people have
in the eye
those
to
devices.
restore vision to the blind. in a
Academic
fairly
labs have
rudimentary
recently
way.
shown that
Tell
you can do
more later.
better with stimulation. You can treat
In
better
addition, you can use the
if
same
you
technology
also are able to record
in
the
the
state
brain.
of the brain, say from motor cortex, and use that to shape the pattern of
for
stimulation.
example, to restore the sense of touch or to restore vision.
Deep brain
And I'm gonna say
stimulation, or
very briefly
DBS, has
about
also been
that
used for
later.
dystonia. It is already approved for
Let's start,
dystonia
with
and
the sense of
obsessive
touch.
compulsive
Consider
disorder.
this
And we
little
think,
bit
again,
of tissue
closed loop
that,
therapies
of
can
brain
do
that I
better.
just highlighted
And in
here.
fact, for
It's at the border
epilepsy, there's
between
already a
motor
commercial
and
product
somatosensory cortex.
that does this kind of closed loop
Blow that
seizure
up.
detection and disruption. Although it
What
does
you
it
can
with
see
only about 8
is that
electrodes.
somatosensory cortex has a very special
There are
property. It
many
has
other,
what we refer to as a spatial map.
Many other diseases.
And what I mean by that is that there are regions that encode the palm of the hand and each of the 5 digits, for example.
We'll get
So if we were to stimulate at one little location, say in the thumb part of the cortex, the person
There are a
would
number
feel
of other
the sense of
neurological
touch and
disorders
pressure
where
on the
DBS
thumb.
has
Or if we were to
promise,
stimulate
but it's
two
still in
sites,
investigational
on the
stage,
palm,
like depression,
in the palm area,
chronic
cortex,
pain,
you might feel a
tinnitus.
couple of points of touches on your hand.
Now, even though
This
these
kind of technology
diseases
has been
are currently being
demonstrated
treated with these big
in many academic labs.
DBS electrodes like
And
you've seen,
in a recent,
we think that
really
there's a
nice paper
potential
shown
here for the kinds of devices we're designing. Individualized, highly focused treatment that will reach broader patient populations and be able to be more effective in the way that they treat these disorders.
Grasping an object, improve
Lastly,
the ability to pick
I want
up
to tell you
and place
about
objects with the robot. So this is the kind of thing that can really
not
help
just
decode.
sensory input and motor output,
So
but
imagine what we could do
about thought.
if we're able
So
to take our device and cover
there are
all somatosensory
parts of the brain where we
can
know
give
that there's
rich
neural activity
sensation
that
of
encodes
objects and
the
haptic
things that we're
feedback when
thinking
you're
about.
manipulating objects.
And
We can maybe
one great
feel
example
different
is an area
textures.
called the hippocampus.
But it's not
The
just about
hippocampus
improving the user
is involved in memory
experience.
formation,
It's
and
also
it helps
about
store
getting to the level of functionality
episodic
that we
memory,
want.
things that you remember
Imagine
from
for a
your life.
second, imagine typing.
It also has
Now
a
imagine
particular
typing
kind of
with your
memory
fingers
for
and that's
locations and views
That's gonna be
that
pretty
you
hard.
know.
So that haptic
For example,
feedback, that sense of
it'll have cells that
feedback
represent
during movement is
places
gonna
in
be
your own
important
home
going forward.
or in a city that you know well.
And
So imagine that you had that you could
that
record
sensory
from
feedback,
a collection of neurons
and
in
we
the
can also
hippocampus
potentially
of somebody
provide
who
visual
lived in San Francisco and knew it well.
visual cortex,
Then it's
just
likely
like
that they would have
sensory
some
cortex
neurons there in the
has maps.
hippocampus that
So,
represent
there's
various
spatial map in
locations
visual cortex.
in Golden Gate Park.
It's here in orange in the back.
And so
So, for
if
example,
that
to
person
simulate
were to take
a
a
particular
car ride,
point
for
in
example,
cortex,
from the
we
ocean
might see,
through the park,
flash of light,
you would see those
in
neurons
the
fire
punching
in
spot
order
in front of them.
as they took
And
that
this was
ride.
demonstrated many years
First a
ago,
neuron that maybe represents a view of the ocean,
by
and then the
neurosurgeons and
bison
it's
in their
been used in
paddock,
academic
and
labs,
so on.
and then we call that little dot a phosphate.
All right.
And if you
So
stimulate
I've told
another
you
area,
about
you
the
get a
way that
phosphate.
the brain represents information, and that
So
these
the idea here is that you
these
could
sorts of
stimulate a bunch of different areas,
encoding
and
methods,
you could create kind of
representations in the
like a
brain
dot matrix
are things that we can
image
learn to
of the
decode.
visual world, which could provide
And I've
a
told you about some of the
rudimentary
applications and how
And
they
there
might
are
work.
academic labs and even companies that are working on technology just like this.
As the device technology gets
There's
better
just
and
one
better,
map of visual cortex.
and as
Actually,
we
there are a
get
bunch
more
of
and more
different maps.
experience with
It's a
those
good example of
devices,
how the brain works.
we
It's a
and
spatial
other
map,
researchers
but they're
will be able to
they're also
bootstrap
maps telling
off
you
of
about
those
the
advances
orientation of
to reach
edges.
other brain areas
There are maps telling
and
you
other
about
applications.
colors.
That's
There are
what
maps
we're trying to do.
telling you about the size and speed of objects moving.
Neuralink's goal,
What we
It's a-
want is a device that has sensors that are
neuroscience has
small
shown
enough, electrodes that are
that
small enough,
a wide
and high
variety
enough density
of information
that we can
content
tap
is
into that
readily
rich
available in the brain.
collection of
We
maps
know, for example,
with our
that there are
stimulation
signals
devices,
that encode
so that
speech
we
and
can do
language.
better than just dot matrix.
There are signals that
so
encode
that
your
we
mood.
can actually create
There are signals that
rich
encode the
visual
sense of
feedback
pain
for the blind.
when you're
That's
hungry
the
and when you're thirsty. There are signals that encode your
But just,
memories,
again,
and even
one more
esoteric
example
things
of the
like
way that these
mathematical
devices
reasoning.
can be used.
What Neuralink
So I've
wants
talked
to
about
do
recording
is to give people
signals, and I've talked
the
about
ability
stimulating.
to tap into those
You can combine those
representations,
two to treat a
to get
variety
back better
of
access to that
neurological
information,
disorders.
both to repair
Max talked
broken
earlier
brain
about
circuits
deep brain stimulation
and also
to treat,
to
say, for example,
ultimately
Parkinson's disease.
give us
And many people have
better
those
access
devices in.
to
Academic labs have
better
recently
connections
shown
to the
that you
world,
can do better
to each other,
with stimulation. You can
and to
treat
ourselves.
better if you also are able to record the state of the brain, say the motor cortex, and use that to shape the pattern of stimulation.
All right, thanks.
Deep brain stimulation, or DBS, has also been used for dystonia.
we're gonna take
It
a
is
risk here
already
and just do
approved
some
for
Q&A,
dystonia and obsessive compulsive disorder. And we think, again,
that's
closed loop
hopefully
therapy
was,
is better.
a good
And in fact, for epilepsy, there's
understanding
already a
of
commercial product
the brain.
that does this kind of closed loop
Yeah,
seizure detection.
nice work, guys. It's like,
Although it does it with only about 8 devices.
that's the
There are many
very proud
other,
Neuralink team. It's done amazing work.
Many other
And
diseases.
yeah, it's a really smart group.
Oh, no. All right.
There's a lot more there's a lot more really smart people. So what you're seeing here is the outcome of a lot of hard work
There are
by
a
the
number of
Neuralink
other
team.
neurological disorders where DBS has promise,
yeah, I think it's
but it's still an
some pretty impressive
investigational
stuff.
stage.
So
like depression,
we can
chronic
take some
pain,
more questions from the
tinnitus.
audience. It's the lights are bright, so you might have
Even
to
though
yeah.
these diseases
just
are
take it
currently
over.
being treated with these big DBS electrodes like you see, we think that there's a potential here for the kinds of devices we're designing. You can individualize
This is
highly
a really
focused
interesting
treatment
question.
that will
So
reach broader
it's
patient
definitely too
populations
early
to be able to be more
to really
effective
think about this.
in a way that they can.
There's, I mean, you know, I don't.
I think we'll hold
Lastly,
up in the custom code
I want to tell you
immediately.
about
But I think they,
not just
I mean,
sensory
it's
input motor output,
conceivably that
but
could be
about
some kind of app store
philosophy.
thing in the future,
So
or some sort
there
of
are
platform
parts of the brain
with
where we
like a very
know
rigorous
there's neural activity that encodes
verification
things
of
that you're
the
thinking.
application.
And one great example
But
is
yeah,
an area
I
called
mean,
the hippocampus.
I think this is certainly not meant to be
It's
sort
involved
of
in memory
a
formation,
closed system.
and it helps
Ultimately,
store episodic memory,
if we can
things that you
enable
remember from
others
your
to
life.
contribute
It
with
also
that,
has
that would be
a particular kind of memory for
We should have one more
locations
thing to this.
and
We've had
views
some
that
discussions
you
like
know.
It might be that if you want to build an app or a business on top of it, like a brain-enabled API, then your business model can't be advertised.
So imagine
for example.
that
That's like it's very important to us that this is like that this turns out well for everyone, and so there's thinking like that going
San
on.
Francisco and do it well, then it's likely that they would have some neurons there in the hippocampus that represent various locations in Golden Gate Park. And so if that person were to take a car ride, for example, from the ocean through the park, you would see those neurons fire in order as they took that ride.
There's no doubt that
First neuron that maybe
plasticity will make
represents the view of
things.
the ocean, and the bison
So
in
the
their
question
path.
was whether neuroplasticity will help or hurt our effort.
So
And I think there's no doubt that
I
it will
told
help.
you about the way that the brain
First of all, there's
represents
just the
information.
fact that you have to learn how to use these devices.
These sorts
But
of encoding methods.
for example, in work that we did in my lab earlier, we showed that you
I think
can
we
write in
learn.
information that isn't perfect. It doesn't get that map
And I've
perfect.
told you about some of the applications
Or even it can
and how they
be
might
somewhat
work.
quite different from the map. But ultimately, you can learn to use that through plasticity.
As the
And,
device technology
It's
gets better and
so
better.
there's going to be a lot
And
of
as we
learning
get more and
required,
more experience
and
with those
the
devices,
ability of the brain to adapt to new
and other
information,
researchers
and in
will be
particular,
able to
the ability of the
bootstrap
brain to
off
take
of those
information that
advances
comes from multiple sources
reach other
and
brain
merge it
areas
in an effective way
and other applications.
is, I think,
That's
the kind of thing that really will facilitate complex new
Neuralink's goal
tasks with these devices.
It stands to reason that the neurons are responding to electrical pulses. So as
of information
the
content is readily
electrodes
available in the
providing
brain.
electrical pulses,
We know, for example,
the neuron
that
and
there are
electrical pulse
signals that encode
is a neuron.
speech and language.
It just thinks it's a
There are signals that
neuron,
encode your
and it's
mood.
going to
There are signals
for
that
sure
encode the sense of pain
adapt dynamically
when you're hungry
because it
and
just
when you're
sees
thirsty.
electrical pulses and it's
There
going
are
to
signals that
respond
encode
to
your
those.
memories and even esoteric things like mathematical
Yeah.
reasoning. What Neuralink wants to do
I mean,
is to
Jesus.
give people the ability
I mean, you'd have really no
Tap
escape.
into
We
those
could not do that. That would be
get better
ethical
access
barrier.
to that information, both to repair broken brain circuits and also to ultimately
So the question is,
give us
if this will not be
better
advertising
access
driven, which I think would be unwise,
to better connection
then
to the
how
world.
will it be paid for?
to each
Essentially, is
other,
that correct?
and to ourselves.
How will we ensure that it's broadly available? I think that the cost of these
Thanks.
brain disease or brain injuries is extremely high to society. If you have to take care of somebody or if they need comprehensive medical care or hospice, this is actually very, very costly to society. So I think the economics of solving for that make a ton of sense. And if you enable somebody to work and be productive, contribute to the economy, I think that will. I think that the economics of that will easily pay for itself.
So what you're saying here is the
And then in the limit, of course, if you want to be symbiotic with AI, you'd be like, I think it's safe to say you could repay the loan with superhuman intelligence. I think it's a safe bet. So I think the economics of this will work out. And the first order is really just to make sure that it works and works safely. And then I think it'll really be the option of the person. But it is critical that this be, sort of, as we talked about before, like a LASIK-like device. If this has to be done by a neurosurgeon, it cannot be scaled. There's just aren't enough neurosurgeons. So it must be just as one wouldn't want sort of like a hand operated laser for an ophthalmology situation. You really want the robot doing it with precision. The same thing goes for the brain interface.
If we can enable others to contribute, whether they're at Neuralink or not, that would be a good thing, for sure.
Just add one more thing to this. We've had some discussions, like, it might be that if you want to build an app or a business on top of it, like a brain-enabled API, then your business model can't be advertised.
The question is, have we
That's like, it's very important to us that there's just like, that this turns out well for everyone, and so there's thinking like that going on.
So I think first it's important to say that we regard any chip implant, even if it's in a rat, as a very serious thing. So we care. We even care about rats, even though they have the Black Plague and everything. So like, they arguably have some karmic payback.
Yeah, there's no doubt that
but nonetheless,
plasticity will make
we care about rats.
So the question was whether neuroplasticity will help
and then
or
we're
hurt
extremely sensitive
our efforts.
with
And I think there's no doubt that it will help.
monkeys.
First of all, there's just the
University of
fact that you have to learn how to
California
use these
at
devices.
Davis
But,
for the monkey.
For example, work that we did in my lab earlier, we showed that you can write in information that isn't
the results
perfect, it
have
doesn't
been
get that map
very
perfect.
positive.
Or even it can be somewhat quite different from the map.
I know this is a
But
sensitive
ultimately,
subject.
you can learn to use that
Yeah.
neuroplasticity.
But I think it is.
You know, there's going to be a lot of learning required, and the ability of the brain to adapt to new information, and in particular, the ability of the brain to take information that comes from multiple
wish that we didn't
sources
have to
and merge it
look
in an
at
effective
that,
way.
right? We just wish that wasn't
is,
like a step in the process.
the kind of thing that really will
but it
facilitate
is. It's a very
complex
important part in the research and development
tasks.
process to produce
It's a sensory
better
sense.
options for human patients.
The neurons are responding to like
Try to be very thoughtful and follow the 3 R's of reduction, replacement, refinement of the laboratory.
neuron as electrical pulse is
Try to be
is a neuron.
very careful and thoughtful
Just
about it and
thinks
do
it's
it
a
as
neuron.
efficiently as possible.
And it's going to
Because we believe that the
for
benefit
sure
to
adapt
humanity is in the
dynamically.
end, like the
because it just sees
benefits outweigh the
electrical pulses,
negatives.
it's going to respond to that.
The questioner also asked about the results, and
Yeah.
there is a paper available, I think now, soon, that has some of the results in it.
I mean, you'd have really no escape. We cannot do that. That would be. Monkey has been able to control the computer with its brain. Just, FYI.
I didn't realize we were running that result today, but there it goes.
Which I think is the point. The monkey's going to come out of the bag. So how will we ensure that it's broadly available? Well, I think that the cost of these brain disease or brain injuries is extremely high.
Can we speak about the FDA path that we want to pursue and how we work with the scientific community?
If they need comprehensive medical care,
Yeah,
or
sure.
hospice,
Well, did you want to start with
very
FDA?
costly.
Well, I was also say, like, we're under no illusion that we think we can do all of the science required for this ourselves. Like, there's an immense amount of neuroscience to be done with these devices, and there's a huge amount that we have to learn about the brain, and that's going to be a much larger thing than just neuro. And we want to get these tools into the hands eventually at the right time. That we're still a very small company just focused on getting our first version, so we have to be laser focused on that. But we want this to be a thing that is much larger. Like, we want this to be a field, right? We want this to really fuel advancement of the field. Because the most important thing is not that, like, Neuralink is this, like, one specific place, but that it advances all of it. And for the FDA, there's a pathway. We're pursuing an early feasibility study, IDE, and there's the FDA actually put out draft guidance in February that's very specific to the type of thing we're doing, and it's pretty prescriptive. It's a checklist of what they want to see, and there's a lot in it. You have to show that it's going to be expected to be safe and biocompatible and stable, but you work through that and you get the documents.
People in academia right now are quite constrained in working with the Utah arrays. That's the most advanced thing in academia. And our system is at least 100, arguably 1,000 times. Well, at least on the order of 100, actually. Relative to the Utah array. 2 orders of magnitude improvement at the experimental level. And so I think it probably would make sense for us to make more of the robots and provide the chips to academia to further the science. Sure. Okay, it's hard for me to see.
Sure. The question is, have we implanted chips in animals? And if so, what are the results? So first, it's important to say that we regard any chip implant, even if it's in a rat, as a very serious thing. So we even care about rats, even though they have the Black Plague and everything. So like they arguably have some karmic payback.
Sure. What is the best way for academics to get in touch with us to collaborate on the field
and then we're extremely sensitive with
First, if anybody out there has technologies or ideas that they haven't heard us talk about today, that they think could be useful for us, they should reach out and tell us about it. We're always interested in new technology and new things that are happening.
I know this is a sensitive subject.
As far as getting the academic community access to data, for example. This is something that we are committed to doing. The details of the pathway on that aren't fully worked out. There are a number of options. And to be honest, if you have ideas about ways that anyone in the academic community thinks that it would be good to engage with us, we're willing to listen, and we'll pick one or two, and we will make it possible for the technology that we're working on to have a very broad impact on the field. That's definitely
the 3 R's of reduction.
Yeah, I mean, the things that sort of really drive the technology are advancing the chip design, the software on chip and for interpretation of the results, material science especially for the coatings of the electrodes, like how do you have a long-life electrode.
The questioner also asked about the results,
This is quite a difficult thing to get that coating, get the materials right, and then the application of materials for the something that you want to be, because you want these electrodes to last for many decades in the brain. But this is quite a difficult environment. It really wants to grow. So having the right coatings is incredibly difficult.
The monkey's going to come out of the bag. So he is. Yeah.
Right. Do we consider longevity a solved problem? Definitely not. So I think the longevity is one of the key questions, and it's difficult to say until you actually have an encounter how long does it last. And then if it does start failing, so failing the nine ring, or going for the bad ring. So
and that's going to be a
I
much
think
larger thing that goes through.
there's not enough time yet to actually say whether it is
eventually at the right time,
a long time. It also makes sense to have accelerated life testing of the electrode, so in a non-brain situation, so figure out something that's actually a worse environment in the brain, and actually, which is actually quite a difficult environment for the chip. So, and electrodes.
For the FDA,
find something that's even worse and have accelerated life testing. That's one of the key things. And then we then need to confirm that.
And there's the FDA actually put out draft guidance in February.
I mean, the latest results are quite promising, but it's too early to reach.
And there's a lot in it. You have to show that it's going to be
we've just recently seen what we think is a remarkable breakthrough, but time will tell.
People in academia right now are quite constrained in working with the Utah arrays. That's the most advanced thing in academia. And our system is at least...
How will we address the mechanical mismatch of the electrodes and the brain? Essentially because the cells are like jello and electrodes are really hard. And so you have a big stiffness difference between brain cells and metal electrodes.
It makes sense for us to make more robots and provide the chips to academia
yeah, I mean, that's part of the reason, one of the reasons why we went towards flexible materials. Like, there are a lot of different kinds of probes out there right now. If you look it up, and that's the main purpose of going flexible and also going smaller. So as I said, that we're really trying to make it as invisible to the brain as possible. And then on top of that, as was mentioned, coatings. So all of those combined, we're hoping to significantly decrease that immune response.
But essentially, you have something with high modulus and something with low modulus. But if you make the high modulus thing very thin, it becomes quite flexible.
Sure. When's the best way of academics to get in touch with us to collaborate?
So I'll try to answer the question at the back there. It's hard for me to see behind the camera.
Yeah.
So, first, if anybody out there has technologies or ideas that they haven't heard us talk about today, that they think could be useful for us, they should reach out and tell us. We're always interested in new technology and new things that are happening. So that's the first.
So I think summarize the question, like essentially if we look at like higher order feedback where it's sort of at the whole limb level or combination of limbs or a whole order ladder as opposed to an individual crossbeam or something like that. Okay.
Yeah, I think that, of course, that's a stimulation result, not a recording result. And it may have something to do with the kind of low resolution of the stimulus, that the psychophysics of that, it's hard to perceive it as a complete letter, but you get filling in of motion that helps you perceive the object. Right? That's kind of sort of my thinking of what's going on. And so, I think these are the kinds of questions that honestly we haven't yet addressed. When I talked about visual stimulation and the kind of rich visual stimulation that we want to, just to be clear, that was aspirational. And so, come back and ask us in a little bit.
Yeah, but there are, this is the, there are like individual neurons that you can trace to particular names and concepts and people, at kind of advanced long-term level, I think people would have kind of like if two people had a neural link, you'd be able to effectively have a sort of really high bandwidth telepathy, or actually technically going over radio waves, but you could actually communicate at a sort of complex meme structure level, using the Dawkins version meme. So then you could really have like potentially a new kind of communication. It's sort of a conceptual telepathy, essentially. Must be conceptual. I'll try to answer something in the back. I can hardly see you, but anyone in the back there, basically. If you talk.
A long time with the particular. It obviously makes sense having accelerated live testing of the electrode, so in a non-brain situation, so you figure out something that's actually a worse environment than the brain, and actually, which is actually quite a difficult environment for a chip. And electrodes. Find something that's even worse and have accelerated live testing. That's one of the key things. And then they need to confirm that in an actual brain. I mean, the latest results are quite promising, but it's too early to reach conclusions. We've recently seen what we think is a remarkable breakthrough, but time will tell. Sure. How will we address the mechanical mismatch of the electrodes and the brain? Essentially because the cells are like jello and electrodes are really hard. And so there's a big stiffness difference between brain cells and metal electrode.
Okay, what's your answer to what do you think we should do? I mean, we're open to ideas here. The overarching objective is to make the future better, aspirationally, and to hopefully not pave the road to hell with good intentions. But I think the road to hell is mostly paved with bad intentions.
That's the main purpose of going flexible and also going to smaller. So, as I said, we're really trying to make it as invisible to the brain as possible. And then on top of that, as was mentioned, coatings. So all those combined, we're hoping to significantly decrease that immune response.
But essentially, you have something with high modulus and something with low modulus. But if you make the high modulus thing very thin, it becomes quite flexible. Moment of inertia. So I'll try to answer questions at the back there. It's hard for me to see behind the camera.
Big question.
Yeah, I think that it's a big philosophical question. What will? It's hard to say what the future will be with something like this brain-machine interface. I doubt that we would be able to eliminate all suffering, and it actually may be ultimately utterly dystopian if we do eliminate all suffering.
If we look at like higher order feedback, where it's sort of at the
there's like, generally like stories about utopia turning into dystopia.
Or a whole or ladder.
But I think we can definitely make a significant difference, and we can address,
of course, that's a stimulation result, not a recording.
Humanity can address
it may have something to do with
a
the
lot
kind
of
of
the
low
suffering that occurs in the
resolution
world
of the stimulus,
and make things a lot better.
The psychophysics of that, it's hard to perceive it.
A lot of times people are quite sort of negative about the present and about the future, but really, I think if you're a student of history,
these are the kinds of questions that honestly we haven't yet
when else would you really want to be
When I
alive?
talked about visual stimulation,
Now's the
and the
best
kind of
time.
rich visual stimulation that we want to, just to be clear, that was aspirational. And so, come back and ask us in a little bit.
Those who think the past is better have not read enough history.
Yeah, but there are...
Okay, way in the back there, I see actually can see a hand, yeah.
There are like individual neurons that you can't trace to particular names and concepts of people, and at a kind of advanced long-term level, I think people would have kind of like if two people had a neural link, you'd be able to effectively
I think
have
that
a sort
DJ
of
should
really
answer
high
this, but
bandwidth
so no.
telepathy.
No.
It doesn't run on AWS.
I'll also say that you often have very tight latency constraints in this.
Yeah,
You
exactly.
really have to run locally.
Yeah, so the question is, how are we doing the back-end computation? What are some of the methods that we're doing it? So as Max just mentioned, latency is something that we do want to minimize as much as possible, especially in the context of doing closed-loop BMI, so being able to record and also stimulate and put information back into the brain. So in order to make sure that that latency between the end-to-end system is minimized, we need to have all that computation locally. So that's one instance of the evidence of spike detection that you saw that's slowly progressed from computation from the computer onto the integrated chip is something that we strive to do as well with closed-loop BMI algorithms.
Yeah, I mean, essentially the vast amount of the computation is actually done locally on an ASIC, effectively. So the amount of data that needs to be communicated beyond the body or the brain is really distilled down to a small amount. And as DJ was saying, like, especially important for if you want to say give someone who's a tetraplegic the ability to type at 40 words a minute, which is one of our goals, and that requires a very low latency feedback loop.
I think last one.
Okay, last question. Okay, go, yeah, fire away. Okay, this is a few questions packed in there. So one of the first question was, essentially summarize what you're saying is like, what's the ratio of electrodes to neurons? Because you wouldn't want a 1-to-1 ratio because that's a lot of electrodes. So you really want to actually have that ratio be as big as possible, and ideally at least 100-to-1, maybe 1,000-to-1, ideally. So, because the bigger the ratio of neurons to electrodes, the fewer implantations, it's going to be just way better. So, for sure you'd want to read a whole bunch of neurons and then be able to stimulate neurons or a cluster of neurons by varying the field potential, so that you don't need to have a 1-to-1 stim or read ratio. Ideally, 100-to-1 question. You guys want to add?
I guess I would
or more.
I think it's important to add to that any answer we give to what's the right number of electrodes at this point is speculation.
We would be able to eliminate all suffering, and it actually may be ultimately oddly dystopian if we do eliminate all suffering. That actually may not be a true utopia.
That's part of the. I mean, but the point I'm trying to make though is that this bootstrapping that we anticipate is going to happen. We're going to put in devices that are going to be lower level. From that, we'll be able to find out the information content and information density in the areas that we're looking at with the electrodes we have, and we'll be able to bootstrap up from that. So, I actually believe that we are the ones that are going to be able to answer that question without speculation.
And also, when you look at the anatomy of the brain is mostly silent. On average, a classical electrode can see somewhere between 0 and 4 neurons electrically by different waveform templates. But when you just look at the anatomy and the distances, you'd expect it to see more like 1,000. And so this question of why is the brain so silent is an interesting one. And one of the hypotheses is that there are a lot of neurons that have very narrow receptive fields that only fire when they have very high information content updates with respect to something specific. And one of the challenges of spike sorting is that you can't tell, you can't tell apart another spike of a neuron that you think you're reporting from with, that was the first time I heard from that neuron specifically that I don't know is there, right? And as you have these long-lasting chronic devices, you'll be able to get more of that out.
I'll also say that you often have very tight latency constraints in this.
I think it's going to vary. electric neuron density is going to vary quite a bit depending upon what part of the brain it is as well. If it's sort of somatosensory is probably like a pretty big ratio. Like you can get pretty impressive results by controlling, essentially pressure with your brain. You don't need very many electrodes for that. So, and there's a lot of neurons in the sort of motor cortex. So, I think there's some cases where you can have, I don't know, this is really speculation, of course. I mean, some places where you could have maybe 10,000 to 1, and some places where you want maybe 10 to 1. I suspect it will vary quite a bit.
I just really quickly on, I think Dan's question, longevity is a really important question that we think about all the time. I don't think that we're releasing histology in the paper today, but I think that just to put pressure on this team, I think that we're running that around SFM probably. There's some really cool stuff in progress.
All right, thanks everyone for coming. Okay. Great questions.